Okay, hello, I'm Catherine. Today I will be presenting my Lab 5 for Physics 2. So starting off with the introduction and the purpose of this lab. The purpose is to study the effects of Faraday's law by using a magnet through an aluminum foil tube, so specifically a bar magnet, and then making a tube out of the aluminum foil. And in order to do this, what we'll have to do is apply the principles that we learned in class about the concepts and behaviors of Curly electric fields. So after running the experiment, I found that my experimental value result was 1.02 seconds. And then when I did the computational model through GlowScript, I found it to be 1.07 seconds roughly. I think when I went through it, it was 1.065, so 1.07 seconds. The principles that I used throughout this lab include Faraday's law, Biot-Savart law, Newton's second and third laws, magnetic force, magnetic flux, and the superposition principle. So going into the experiment, the first thing that I did is I took the dimensions of the tinfoil tube that I made. So the length is 0.27 meters, the width is 0.02 meters, and the inner radius of the tube is 0.015 meters. So you can see on the right side, I have my trials, timed it with my phone, took the average at the end, found my average was 1.02 seconds, which is what I explained before for my experimental model. And the next question, follow-up questions to this part of the experiment were, why can't we use a ferrous tube, for example, a steel pipe? And the reason for that is since steel is magnetized, the magnet would attract to it rather than fall as it's supposed to. So we'd have nothing to time the fall there. And then what happens to the magnet? How does this compare to a magnet falling in free space without a tube? So basically, because there's a magnetic force with the tinfoil, it's opposing the force from gravity when the magnet is falling through it, which is making the magnet fall slower through the tube than it would freely just due to gravity. So moving on to the GlowScript, tried to highlight some of the more important portions of where I changed the template code, but here is just the tube measurements that I just explained before. Next, I used the equations that we used in Lab 3 to calculate the magnetic field of the bar magnet. So that's kind of seen in more so the second half of this image. And then from there, I moved on to calculate the rate of change in the magnetic flux as the bar magnet fell through the rings. And then for part 4, I added the force due to gravity and calculated the current using Faraday's law. Moving on, this is just more from the template. And then for step 5 and 6, we use the magnetic force with Biot-Savart law, and then calculate the net force and the magnet's position and velocity using Newton's laws. So here are the results to my computational GlowScript model. You can go through my GlowScript and actually play through the result, but these are just some captures of it. The graph is our velocity over time graph, and you can see the way it changes, which I'll go into in a second more. So based on this, we were asked to interpret the results. I found that blue meant a counterclockwise current versus red indicated a clockwise current. Next, when the magnet is flipped, the thin rings current flow in the opposite direction. And then I just noted that our experimental system was not very far off from the computational system. So that being said, though, the experimental system is a good way of doing this experiment, but the computational system typically is more accurate because you don't have to deal with outside factors. And then next, going back into the shape of the graph, like I mentioned before, it shows that the magnet falls and accelerates before and after entering the tube, but then falls at constant velocity inside the tube. So that's this part of the graph where you can see that it dips to just below this -30 at maybe, let's say, 0.7 seconds. And then it goes back and then it continues at constant velocity. So in conclusion, we had a few questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So my answer to that was if the resistivity of the conductor was reduced to zero, the current would increase, followed by the magnetic force increasing and eventually overcoming gravity. And then the magnet would remain in the tube and not fall through. Next question, what if holes or slots were cut into the tube? How would this affect the ring currents in your own model? So my answer to that was if there was holes or slots cut into the tube, the current would decrease due to the gaps, and this would just result in the magnet falling through much faster, more similar to how it would just fall through in like regular gravity. So that concludes everything. Thank you for listening.